Hi, my name is Alex Keller and I will report on how Quasi-Monte Carlo methods may enhance hardware for artificial neural networks. This is joint work with my colleague Matthijs van Gersbilk at NVIDIA. Let us briefly review some basics of neural networks. Given an input vector A0, an artificial neural network computes an output vector AL. It does so by means of a computational graph whose vertices are neural units connected by weighted edges. These neural units are organized in layers. As depicted here, all neural units of one layer are connected to all neural units of the next layer, and hence the layers are called fully connected. Each neural unit computes a weighted average of the activations in the previous layer. If the average is negative, it is clipped to zero. Otherwise, the neural unit is called active and passes on the average. The weights, in fact, can be learned from pairs of training data. Given an input A0 and a desired output AL, the approximation error is propagated back through the network by computing the weighted average of the error of all active neural units in a layer. If a neural unit is active, the weight of an edge connecting it to a previous neural unit is updated by the product of the learning rate lambda, the error at the active neural unit, and the activation of the previous neural unit. Now, the human brain has about 10 to the 11 nerve cells, but only up to 7,000 connections per neuron, which means that the human brain cannot be fully connected. Hence, we want to look for algorithms that are linear in the number n of neurons. However, the number of weights in a fully connected layer is already quadratic. Unless we bound the number of connections of the neurons by a constant, this would result in an algorithm of complexity linear in time and space. As an example of a modern artificial neural network, let's take a look at the principles of speech recognition, where the task is to transform the spectrogram of an audio snippet into an array of letter probabilities over time. The audio features, located in frequency and time, are processed by a sequence of layers of blocks, each consisting of a temporal convolution followed by a fully connected network and the rectified linear unit activation function. In the final step, for each instant in time, the features are reduced to probabilities of letters, again using a fully connected layer. Taking a look at one such block of a temporal convolution in a fully connected layer and giving a piece of audio, the averages C computed by the convolutions could look like this. Here, red means negative, green is positive, and blue is exactly 0. The activations computed by the rectified linear unit then clip all negative values to exactly 0, showing a lot of blue, meaning that in fact there is a lot of sparsity in the computation. In order to find an algorithm linear in time and space, we write the activations AL, which are the nonlinearity applied to averages, as averages CL of nonlinearities. This is just equivalent. In the continuous form, the averages relate to high-dimensional integral approximation, which allows us to interpret neural networks as sequence of linear integral operators applied to nonlinear functions. From the domain of integral equations, especially the domain of computer graphics, we know how to compute such sequences. Following photons, we trace paths from the sources to connect to the sinks. So why not try to represent artificial neural networks by paths as well? Looking at the computation graph of an artificial neural network, we can trace paths from the outputs to the inputs. And we can even guarantee to cover all inputs and outputs. Now, computing only the colored part of the graph yields a complexity that is linear in the number of paths times the depth of the neural network, and hence linear in the number of neural units. To create these paths in a trained neural network, we explored an invariant of the rectified linear unit. In fact, scaling the activations by a positive factor f and dividing the average by the same factor leaves the result unchanged. Choosing this factor as the one norm of the weights of a neural unit These factors can be propagated through the neural networks, leaving the weights of each neural unit as a discrete probability density. This process can be termed network normalization. Given a trained normalized neural network, it is straightforward to trace paths from the output back to the inputs by simulating the discrete densities. As they define a partition of 1, a uniformly distributed sample xi selects an activation A with its corresponding probability W. Averages then become approximated by the average of the selected activations. This amounts to quantizing the weights of a neural network to either -1 for negative weights, +1 for positive weights, or 0 for omitted weights. This quantization process also is called ternarization. The graph shows test accuracy of a selection of image recognition networks when quantizing them by paths as just described. Along the x-axis we see that there is no notable degradation in test accuracy unless the fraction of sampled paths become less than 10% of the number of connections in the fully connected layers. For more state-of-the-art neural networks like residual networks, the simple rapid quantization procedure comes into reach of a process that is called trained ternary quantization. For different depths of residual networks, both quantization approaches achieve about the precision of the unquantized networks. With respect to the number of bits required to achieve this quality, our instant quantization is off by a factor of 2.5. However, this does not require retraining, which is rather costly. So quantization of a neural network by paths still requires to train the full network, which raises the question whether neural networks can be sparse from scratch to improve the complexity of training as well. We are going to prove the case by going through an implementation. The first step to represent a neural network by paths is to generate the random walks as an array of indices. Therefore, we enumerate all layers and paths. In layer L of path P, the index of a neural unit then is just randomly selected among the neurons in that respective layer. Next, the weights along the edges of a random walk path are initialized with a constant. This is a very notable fact, as in a fully connected neural network this would not work, as all neurons then would act identically and nothing could be learned. Although seemingly a deterministic initialization, why does it work for the sparse networks? Well, the edges that are not covered by the random walks may be considered as randomly selected zero weights in the initialization process. Hence, neural units are unlikely to share the same connections, which makes the constant initialization work. The evaluation, also called inference, of a neural network represented by paths first copies all inputs to an array of activations A and then fills all other activations with 0. The actual computation then loops over all layers and paths where an activation A is updated only if the previous vertex along the P path is positive, meaning active. This is an implicit implementation of the rectified linear unit. It is obvious that the complexity of the algorithm is linear in the number of paths times the depth of the neural network. Also note that all weights are accessed in linear order, which is most efficient memory access pattern on modern hardware. For a simple example of recognizing digits or fashion items in tiny images, training such a sparse-from-scratch network and comparing it to its corresponding fully connected network reveals that only a tiny fraction of paths as compared to the number of connections within the fully connected layers is required to come very close to the test accuracy of the fully connected variant. In the next step, we take a look at parallel computer architecture. Back in the 1970s, systolic arrays were based on simple processing units. As an example here, a multiply and add unit that computes b plus a times x is shown. Both x and b are buffered by a register. Tiling such tiny compute units allows one to parallelize large parts of matrix multiplication at the cost of a certain latency. In fact, Google's tensor processing units are based on this architecture. The name systolic comes from the analogy to the heart pumping in and out blood in a cycle, where in systolic arrays data is pumped in and out in a cycle. The second big concept in parallel computing was the perfect shuffle. Like mixing cards the perfect way, data, in the left part of the graph, was interleaved in the perfect way, and pairs of data then were processed in the right part of the graph. This architecture has many famous applications, including the efficient implementation of the fast Fourier transform. It even has been applied to tiny neural networks. The connection patterns of perfect shuffle appear to be too restrictive, and hence the idea came up to use more general permutations to connect layers within neural networks as seen on the left. The idea behind such architectures are driven by the aforementioned fact that accessing the weights in memory is most efficiently done in sequential order. This access pattern is depicted on the top of the right figure, where 4 weights are loaded at a time. Sweeping over the accumulators on the right, a progressive permutation is used to connect to activations on the left. This activation multiplied by the corresponding weight is accumulated on the right. The permutations have their origins in interleaver design. Taking a look at the visualizations, where a point in the unit square means a connection of the neuron at coordinate x to a neuron in the next layer at coordinate y, you are immediately reminded of the sampling patterns that are at the heart of the MCQMC conference series. The Sobol low discrepancy sequence is an example of such points. It is a deterministic construction of uniformly distant points in the unit hypercube. Looking at the first 2 dimensions of the sequence, a special property is that each contiguous power of 2 sequence of points is perfectly stratified. As an example, we look at the sequence of 8 successive points each, or 16 successive points each. Superimposing the elementary intervals, you can see that in each stratum there is exactly 1 point. Especially interesting is the fact that the Sobol sequence produces Latin hypercube samples. The components of the Sobol sequence are computed as radical inverses, of which the simplest example is the van der Corput sequence in base B. It maps integers to the unit interval by representing the integer I in base B and mirroring this representation at the decimal point, which results in a fraction between 0 and 1. For base 2, we first map to 0, then 1/2, 1/4, and 3/4. In fact, continuous blocks of b to the m points then will be equidistant, and multiplied by b to the m form a permutation. In fact, these permutations are progressive. In general, the components of the Sobol sequence are determined by a general matrix C that is multiplied by the binary representation of the integer I, all in base 2, meaning in the field F2 of 2 elements. The actual algorithm is very amenable to a tiny hardware implementation. For each digit set the integer I, the corresponding column of the generator vector just needs to be XORed with an accumulator. This is in fact very similar to the permutations used to map entries to cache cells in current processors. On the right, we can watch the evolution of the permutations mapping x coordinates to y coordinates. By construction, they are guaranteed to fill all strata from sparse to dense. We will use the components of the Sobol sequence to replace the pseudo-random number generator that created the path indices of our sparse networks. Remember that continuous blocks of lengths of powers of 2 are permutations, so if we choose power of 2 neurons per layer, the permutations of the Sobol sequence guarantee that each neuron has the same number of connections. Here is an example of a sparse classifier network, where the paths are generated by the Sobol sequence. A high-dimensional input vector on the left is condensed to a vector of classes on the right. Each layer has a power of 2 neurons, and each neuron in a layer has the exact same constant number of connections. A second example is an autoencoder structure that is often used for filtering signals. Input and output layer hence are of the same dimensions. Again, all paths are generated by the Sobol sequence. Note that the Sobol sequence easily can be computed in hardware, and hence the connectivity of the network does not need to be stored explicitly. The final example demonstrates the advantage of encoding and network topology by a low discrepancy sequence. As the permutations are progressive, it is easy to add another power of 2 connections. Note that all valence properties are preserved. This way, it is possible to enumerate network topology from sparse to fully connected. To summarize, we introduced the concept of representing neural networks by paths, which enables linear complexity in the number of neural units in space and time, both for inference and training. Other than in fully connected networks, the structural sparsity allows for constant initialization. Encoding the network topology by a deterministic low discrepancy sequence brings together Quasi-Monte Carlo methods and artificial neural network, with the special advantage of ideal linear memory access for all weights, which in combination with the Sobol sequence is very amenable to computer architecture. Thank you very much for watching my presentation.